Welcome to Lecture 10 of Physics 506. In this lecture, we're going to show you how we get the eigenfunctions and wave functions of hydrogen using the operator methods. So let's start with the hydrogen atom Hamiltonian. It has a kinetic energy term. We'll be using the reduced mass, so we're going to denote that reduced mass by mu. It's only about a 0.5% different from the electron mass because the mass of the nucleus is about 2,000 times larger than the mass of the electron. We have the sum of the Cartesian momentum in the XYZ direction squared, and then we just subtract the attractive interaction between the nucleus and the electron, which is given by minus e squared over r. In this picture, you should be thinking about the center of mass of the nucleus as lying at the location of the origin of the coordinate system. Remember, it's this effective coordinate system for the two-particle system. The actual nucleus in this picture would be orbiting on an orbit. In at least a classical situation, it would be orbiting an orbit with a radius that's about 2,000 times smaller than the orbit that the electron has. Of course, in quantum mechanics, we don't really have orbits. All right, so now let's recall that the kinetic energy can be decomposed into its radial and angular pieces. We have the radial momentum squared PR squared over 2 mu plus the angular momentum L vector operator squared over 2 mu R squared minus E squared over R. And we are ignoring the motion of the center of mass, as we mentioned we would be doing. Now, because the Hamiltonian commutes with L squared and LZ, and we can immediately see that because the angular momentum operators really depend just on the angles, and PR just depends on the radial components, and angular momentum commutes with the radial vector R hat. L squared also commutes with the radial component of the momentum, PR. So both L squared and LZ commute. The best way of seeing that is in the Cartesian picture, using the fact that P is a vector operator, as is R, so that vector, and so is L. So vector operators commute with scalar operators, which are P squared and R squared, or the square root of R squared. And because of that, each component of angular momentum will commute with the Hamiltonian, but with angular momentum, we can only choose two mutually commuting operators, and we choose L squared and LZ as the two operators that mutually commute. So what this means is we can simultaneously diagonalize the Hamiltonian, the square of the angular momentum, and the Z component of the angular momentum. And so we write our wave function psi as a radial wave function, tensor product with an angular momentum eigenstate that is an eigenstate of both L squared and LZ. L is the eigenvalue of L squared, such that the eigenvalue for L squared is h bar squared L times L plus 1, and M is the quantum number for the eigenvalue with respect to LZ with an eigenvalue h bar times M. All right, so if we operate our Hamiltonian onto this state vector psi, then because L squared acting on Lm is equal to h bar squared L times L plus 1 times Lm, what we find is that we have a set of Hamiltonians which are indexed by L that satisfy HL acting on psi r is equal to E times psi r. We'll later be using subscripts and other notation for the E, but that's the eigenvalue problem, where HL is PR squared over 2 mu, and now we can replace that L squared operator by the eigenvalue that it has in the Lm eigenstate, h bar squared L times L plus 1 over 2 mu R hat squared minus E squared over R. And this then is the Hamiltonian for each angular momentum state given by L. Now our job is to use the factorization method for each of these HL Hamiltonians to find all of their eigenvalues. And there are two ways in which you can use the factorization method to do this. schematically, and it probably isn't going to make much sense to you when I say it now, we can think about moving through the spectra in a horizontal way or moving through it in a vertical way. In this lecture, I'm going to show you how we move through it in a horizontal way. In the homework, you're going to see how we do it in the vertical way. The vertical way is the standard Schrodinger method. What I'm going to show you is a shortcut that actually gets you to the answer quicker by using the intertwining relationship. And you're going to see that in just a moment. All right, so we need to factorize that Hamiltonian. And it turns out that just with a little bit of thought, you can recognize that choosing the lowering operator, which we're going to denote B hat sub r of L, the r to indicate it is a operator that is acting in just the radial space, and the L is the quantum number index, it's going to equal 1 over square root of 2 mu times PR minus IH bar, and then what's in the parenthesis will be the superpotential. I'm going to write the superpotential as alpha divided by A0 plus beta divided by R hat. Now, the reason why we're choosing that is that when I square that, I will get a constant term, I'll get a 1 over R term, and I'll get a 1 over R squared term. And when I look at the commutator of that with momentum, I will get a 1 over R squared term. So we have all of the elements that we need in which to form the Hamiltonian for the HL, where the potential, if you look at it, has a 1 over R squared and a 1 over R term. And let me remind you, when we do the factorization method, we want to produce the potential up to a constant, additive constant that is going to ultimately determine the energy eigenvalues. Now here I'm using a notation where A0 is equal to h bar squared over mu e squared. That's the Bohr radius. And if you plug in the numbers for h bar, the reduced mass, and the electrical charge, you will find that that Bohr radius is about 1/2 of an angstrom. It's 0.529 angstroms. Again, an angstrom is 10 to the minus 10 meters, or it's 10 to the minus 8 centimeters, or it's a 1/10 of a nanometer. All right, so how do we do this? Well, we've gotten our form that we're going to make for a guess for our BR. We just calculate BR dagger BR and force it to work. Okay, so BR dagger BR is going to have a PR squared over 2 mu. It's going to have a minus IH bar over 2 mu commutator of PR with alpha over A0 plus beta over R hat. And then it's going to have plus an H bar squared over 2 mu alpha over A0 plus beta over R quantity squared. Now, if you remember, the commutator of PR with R hat is minus IH bar because that's a canonical commutation relation. And you can use that to then verify that the commutator of PR with 1 over R hat is just equal to IH bar over R hat squared. So we're going to substitute that in for the commutator. We're going to expand the square, and what we're going to find is we get the following collection of terms. We have the PR squared over 2 mu. We have an H bar squared over 2 mu R hat squared times beta plus beta squared. So the beta is coming from the commutator and the beta squared is coming from the square. Then we're going to have plus H bar squared over mu, because there's a factor of 2 that cancels, alpha beta over A0 R hat. And then we're going to get plus H bar squared over 2 mu alpha squared over A0 squared. Now, we need to have the coefficient of the 1 over R squared term to be H bar squared L times L plus 1 over 2 mu. That tells me beta times beta plus 1 is equal to L times L plus 1. Now, your first notion might be, oh, well, that tells me beta is equal to L. But there actually are 2 roots to this. One of them is beta equals L. But if you think carefully about it, you'll see the second root is beta equals minus L minus 1. We also learned that alpha beta must equal minus 1. We get that when we recognize that if we substitute in A0 is H bar squared over mu E squared, you find that that expression is equal to E squared alpha beta over R hat. And we need it to be minus E squared, so we need alpha times beta to be minus 1. All right, so that tells us alpha is equal to minus 1 over beta, and we have 2 choices for beta. How do we pick? Well, let's take a look at our superpotential. Remember the superpotential, and I'll just move back up to show you what that superpotential is. When we look at that superpotential, it's equal to alpha over A0 plus beta over R. And the limit as R goes to infinity, that's going to equal alpha over A0. And we need alpha over A0 to be positive. Otherwise, our wave function won't be normalizable. That is one of the rules that we have for working with the factorization method. So we need the alpha to be positive, and that means we need the beta to be negative. Well, there's only one choice for a negative beta. That's beta equals minus L minus 1. So we're going to choose beta equals minus L minus 1. And then alpha is equal to 1 over L plus 1. And you can see that will guarantee that the superpotential is greater than 0 as R goes to infinity. So that's it. We've determined our ladder operators. The BR of L is 1 over square root of 2m PR minus I H bar 1 over A0 L plus 1 minus L plus 1 over R hat. And then when you calculate the Hamiltonian HL, you find that it's equal to BR dagger of L, BR of L plus EL tilde, where EL tilde is minus 1/2 1 over A0 E squared over beta squared. Okay, what we use there is we took the expression minus H bar squared alpha squared over 2 mu A0 squared, and we use the fact that one of the A0s is equal to H bar squared over 2 over mu E squared to replace that by, so it's minus 1/2 1 over A0 E squared over beta squared. And then substituting in what the beta squared is, which is L plus 1, that becomes over L plus 1 squared. So we get minus 1/2 E squared over A0, 1 over L plus 1 squared. All right. Now we're going to get the eigenfunctions by using intertwining. So let's first go ahead and take a look at what intertwining is. We're first going to compute these two operators, B R of L and B dagger R of L, in the opposite order. And what that means is we're going to be adding twice the commutator to the result that we had just computed. And what you find is that becomes equal to HL plus 1 minus what we're going to call EL tilde. Remember, the new Hamiltonian is BR of L, BR dagger of L plus EL tilde. And what that tells us then is that we have the same relationship that we had with the A operators and with the factorization method. So we have the normal intertwining relationship. And let me show you how that works. So HL BR dagger, we plug in what HL is. It's equal to BR dagger BR plus EL. I'm going to move that BR dagger into the parenthesis. And then I'm going to pull a BR dagger of L out on the left-hand side. That's going to leave me with a BR of L, BR dagger of L plus EL tilde. The BR and BR dagger are in the wrong order, but that's exactly what order they need to be to give me HL plus 1. And so we have the standard intertwining relationship. When I move a BR dagger through an H, it increases the H index by 1 if the indices of the BR dagger and of the H are the same to begin with. Now we can just use that intertwining relationship to actually construct the eigenstates. We're going to label the energies with n equal to L plus 1. So it's going to be minus E squared over 2A0 n squared. We're going to call that E of L equals, E sub L equals n minus 1. We're going to be labeling those, or E tilde of L equals n minus 1. So if there's a tilde, I'm labeling the energy with L. If there's no tilde, I'm labeling the energy with n. So the state, which is the ground state of HL, satisfies BR of L times that state is equal to 0. It's an eigenstate of HL, so the angular momentum is L, and we just said n is equal to L plus 1, so that state is n equals L plus 1 comma L, and the energy is En equals minus E squared over 2A0 L plus 1 squared, or you could write it as minus E squared over 2A0 n squared. So we can write it in two different ways. We can also, if we want to use the n index rather than the L index, we can write it as BR of n minus 1. Multiplying the state n, L equals n minus 1 is equal to 0. And then En is minus E squared over 2A0 n squared. All right, now our claim is that the state given by n comma L is equal to this chain of B dagger operators, B dagger R of L, B dagger R of L plus 1, all the way out to B dagger R of n minus 2, acting on the state n comma L equals n minus 1. And that is an eigenstate of the Hamiltonian HL with an energy En equals minus E squared over 2A0 n squared. So the energies do not depend on the angular momentum L. All states with all possible values of L are degenerate. I also should point out, if you go and take a look at what the our dagger of L is. It is undefined when L is equal to -1, so I can bring that chain all the way down to L equals 0, but I can't go beyond that. So we're going to have L values that are going to run from 0 all the way out to n-1. All right, so let's check. Let's operate HL on this state n comma L. And also note further that this state is not normalized. We'll get to normalization later, just like we did with the regular factorization method. So HL BR dagger of L, well, that's primed for intertwining. I can move it through, becomes HL plus 1. And then the HL plus 1 is next to a B dagger R of L plus 1. Well, that's also primed for intertwining. I can move it through and make it HL plus 2. And by the time I get to the end, I'm going to have an H of n-1 acting on the state n comma L equals n-1. But the state n comma L equals n-1 is an eigenstate of H n-1. Remember, n-1 is the angular momentum. And the eigenvalue is just given by minus e squared over 2a0 quantity n squared, what we call En. So I can pull that En out because it's a number, and we've just established that HL acting on the state NL is equal to En times the state NL, so it's an eigenvalue eigenvector relationship, and it's an eigenstate of the Lth Hamiltonian with an eigenvalue given by En. So we've actually found this chain of states for all L going from 0 out to n-1, and they all have energy n-1. I just want to point out in the case where L is equal to n-1, there are no B dagger operators. We just start with the state n comma L equals n-1. All right, so the spectrum looks like the following. When L is equal to 0, there's just one state. When L equals 1, there are two states. L equals 2, there are three states, and so forth. And the degeneracies are getting smaller and smaller as the total energies are approaching 0 in the limit as L goes to infinity. All right, we got all of the energies, and you see no differential equation. We really just solved an algebraic equation in order to get all of the energies, all the eigenstates of hydrogen. Again, I don't know about you, but I find this really, really cool. I think it's just so cool that you can do that. All right, our next step is to get at the wave function. And although it might not seem like it, that string of BR dagger operators multiplying n comma L equals n-1 is actually a polynomial in 1 over r hat. And you're going to see that when you notice that the subsidiary condition that BR of n-1 acting on n comma L equals n-1 equals 0 can be rewritten as PR acting on n comma L equals n-1 is equal to IH bar 1 over NA0 minus n over r hat times n comma L equals n-1. This means all of the PRs, once I can move them through to the right so that they act on the state n comma L equals n-1, they're going to create a constant term and a 1 over r term. So we're going to get a whole bunch of these constant terms and 1 over r terms, in fact, many products of those, and that's a polynomial in 1 over r. Now, what we want to do is we want to find out exactly what the form is for those polynomials. And to do that, you should be thinking the obvious way to approach this is going to be by some kind of induction argument. So to organize our work, we have to establish some notation, which, like in the simple harmonic oscillator, uses the answer, so everything ends up being neat. So we're going to write the state NL, which is this string of B dagger operators acting on n comma L equals n-1. I'm using my 20/20 hindsight to write it in the following way. Minus IH bar over square root of 2 mu NA0 raised to the n minus L minus 1 multiplied by NA0 over 2 r hat raised to the n minus L minus 1 multiplied by 2n minus 1 factorial over n plus L factorial times n minus L minus 1 factorial times L factorial over n minus 1 factorial multiplied by an object I'm going to call big L sub n minus L plus 1 sup 2L plus 1 of 2r hat over NA0, all acting on n comma L equals n minus 1. That is defining our polynomial operator, L 2L plus 1 sub n minus L minus 1. The n minus L minus 1 is actually counting the number of B dagger R operators that we have. The factorials are put in to put it in the standard form, which essentially means put it in a form that corresponds to what a dead French or German mathematician did in the 1800s. And what we're going to do, it's a polynomial, so we're going to write it in a power series. Now you see, because we've pulled out this factor of n over a0 to the 2 divided by 2 r hat to the n minus l minus 1, this polynomial is actually now a polynomial in the argument 2r hat over na0, and it has a set of coefficients. So I'm going to call those coefficients a sub j 2l plus 1, 2l plus 1 being the label, and then the argument is 2r over na0 raised to the jth power. And the idea is we want to find a recurrence relation, just like we did with the simple harmonic oscillator for the Hermite polynomials. And we're going to do that by taking a factor of b dagger r of L out from the left-hand side. So what we're going to do is we're going to substitute in what the polynomial is when I have that b dagger factor on when I have the full string going all the way out to the b dagger r of L. And then I'm going to rewrite it using the polynomial that I would have for L plus 1, and I'm going to keep my b dagger r of L explicitly out to the left-hand side. Okay? So again, I want to be sure. Let me go back to the way that this expression looks and be sure that you're clear. What we're doing is we're writing this state n comma L in two ways. We're writing it as the full string, which has this full expression in terms of this polynomial operator, L sup 2L plus 1. And then what I'm going to do is I'm going to take that br dagger of L out to the left, and what remains is n comma L plus 1. So we have a polynomial for that, which is a L superscript 2L plus 3, and it has a b dagger r of L sitting out to the left-hand side of that. So if you look here, what you see is we have the first polynomial. The coefficients are for the 2L plus 1 polynomial because it's a 2L plus 1 sub j. And on the right-hand side, it's the polynomial a 2L plus 3 sub j, because that's the next polynomial, the one where I had just the string that terminated at the L plus 1 b dagger operator. So now what we have to do is we have to bring that b dagger r of L term out to we have to move it to the right. We have to move it through all of these r operators. And the thing that makes it difficult is that b dagger operator has a p in it. So we're first going to ask, if you look at this, the operator that it has to move through for each term in that summation is the term 2r hat over na0 to the n minus L minus 2 minus j. So the idea is, can I evaluate this object? And of course, I have a p term. I'm going to have to move that p term through that expression. And then I have some terms. I have constant terms. And I have 1 over r terms. I just have to collect those terms. Now, when I move the pr through, I'm going to use the add 0 trick to make it a commutator with that r hat operator raised to a power. And I'm going to use the fact that when the pr acts on that state, n comma L equals n minus 1, I know exactly what it gives. So what we find is that those first two terms, 1 over na0 minus n over r hat, that's from when p hat r acts on n comma L equals n minus 1. The term minus n plus L plus 2 plus j times 1 over r hat, that comes from the commutator of p hat with r hat raised to that power. And then the next two terms, the plus 1 over L plus 1 a0 minus L plus 1 over r hat, those are the terms that are coming from the superpotential of the lowering operator. And then we have that factor, 1 over 2 r hat to the na0 to the minus n plus L plus 2 plus j, all acting on the state n comma L equals n minus 1. Now, you can see we're going to have a couple of different terms because some of these terms are constant terms and some of them are 1 over r terms. So we're going to be mixing together different coefficients when we're trying to relate the two polynomials. All right, so we're going to just substitute that in to our expression. Now, the expression we're going to first simplify it, and we find that we get just two terms, n plus L plus 1 over n times L plus 1 over a0, and a minus 2L plus j plus 3 over r hat, and that's all multiplying these other factors and so forth. You should pause the video. Let me just move it back up a little bit. You should pause the video, make sure that you can do this. You can see with the 1 over r hat, I have a minus n and I have a plus n, so those cancel, just leaving behind the L plus 2 plus j. We also have this minus L plus 1 term, and that is going to be adding to the L and it's going to be changing the 2 to a 3. So we end up with a minus 2L plus j plus 3 as the coefficient of the 1 over r hat. And then you can work out what you get, with the 1 over a0, you can pretty quickly see you're going to get an n plus l plus 1 divided by n times l plus 1. Okay, so now we can plug that into the summations on both sides. So what we find, the right-hand side I'm going to just copy, okay? So there's nothing that's happening with that right-hand side. That's just being copied from the expression that we had without the b dagger sub r of L. And then on the left-hand side, I have this expression that we just calculated for each of those particular terms. And I have removed some of the extraneous factors from the right and from the left in putting this together. Okay, so now what we're going to do is we're going to focus on rewriting this so that this next expression that we have is multiplying together some of those different factors on the left-hand side, and then on the right-hand side, at this stage, I'm also just pulling out a couple of constants. What I'm trying to do is I'm trying to get that r hat term to look like the argument of the polynomial, the 2r hat over na0. So I'm just pulling out a 1 over na0, and I'm grouping the 2 with the r hat and so forth. And now what we're going to do is we're going to equate the coefficients of the corresponding powers of j. So what you find is the coefficient on the right-hand side is n squared minus l plus 1 squared over l plus 1 a 2j plus 1, sorry, 2l plus 1 sub j. And let's look at the general case where 1 is less than or equal to j, less than or equal to n minus l minus 2. In that case, I'll get 2 times 2l plus j plus 3 times a 2l plus 3 sub j. And then I'll get minus n plus l plus 1 over l plus 1, a 2l plus 3 sub j minus 1. And then you have to work a little bit carefully to get the edge cases, the case where j is equal to 0, where one of those terms does not contribute, and the case where j is equal to n minus l minus 1, where again, one of those terms does not contribute. And what we're going to do is we're going to look at the ratio of successive coefficients of the polynomials. So we're going to look at the ratio of a 2l plus 1 j plus 1 divided by a 2l plus 1 j. And we're going to just plug in our formula, and I'm plugging it in for the general case. What we're going to do is we're going to divide that general case by an a 2j plus 3, 2l plus 3 sub j. We're going to divide numerator and denominator by that. And what we're going to find after we do that is we have essentially a recursion relation for these ratios of coefficients, okay? You can see I have a ratio of the coefficients on the left-hand side for 2l plus 1, and I have two sets of ratios of the coefficients, one for j plus 1 comma j, the other one for j comma j minus 1. The second coefficient is an inverse because it enters in the opposite form in that expression. So now if you were just given this problem and you had to solve it, you have to go through some pretty nasty algebra to try to get this into the right form to recognize what the solution of this recurrence relation is. But I'm going to do that hard work for you, and I'm going to just tell you that the following is the solution of this recurrence relation. If I look at the ratio a 2l plus 3j divided by a 2l plus 3j minus 1, if I write that as l plus j minus n plus 1 divided by j divided by 2l plus j plus 3, and I take a 2l plus 1 j plus 1 divided by a 2l plus 1 j as l plus j minus n plus 1 divided by j plus 1 times 2l plus j plus 2. That's in the same form as what you were using for this other term. If we do that, then my claim is you substitute into this recurrence relation and it actually works. So let's go ahead and substitute it in. The left-hand side will become l plus j minus n plus 1 divided by j plus 1, 2l plus j plus 2. And now we plug in, we get 2 times 2l plus j plus 4 times the expression where the j goes to j plus 1, which is l plus j minus n plus 2 divided by j plus 1 times 2l plus j plus 4 minus n plus l plus 1 divided by l plus 1. and then divided by 2 times 2L plus J plus 3 minus N plus L plus 1 divided by L plus 1. And now we have to substitute in the inverse of this expression with the J minus 1. And that's a J times a 2L plus J plus 3 divided by L plus J minus N plus 1. Yes, it is a mess, okay? But again, French cooking, this is just simple algebra that we have to go through. They're just many steps, okay? So let's now go ahead and take a look at what happens when we simplify this. You're going to see the 2L plus J plus 4 cancels numerator and denominator. And in the other expression, I'm going to factor out a 2L plus J plus 3 because that appears in both terms. And next thing I'm going to do is I'm going to pull out some common factors. So I'm going to pull out a denominator term of a 2L plus J plus 3. From the denominator, I'm going to pull out of the denominator an L plus J minus N plus 1. And I'm going to pull a J plus 1 out of the numerator. And I'm also multiplying numerator and denominator by L plus 1. So you see what we're going to get in the numerator is 2L plus J minus N plus 2 times that L plus 1 minus N plus L plus 1 times that J plus 1. And in the denominator, I'm going to get a 2 times an L plus J minus N plus 1 times L plus 1 minus N plus L plus 1 times J. Okay? Now, we're going to just expand out those expressions. So I'm doing a little bit of a factorization here. I'm grouping together the terms that have L plus 1. You see there's an L plus 1 on the right-hand side. I just take all of those terms. But you see there's an L plus 1 on the left-hand term that's multiplied by a minus J plus 1. So I'm going to add that J plus 1. Sorry, I'm going to subtract that J plus 1 from that 2 times L plus J minus N plus 2. I'm left with a 2L plus J plus 3. I'm reserving the minus 2N times L plus 1 because I'm going to gather terms that have N's in them. And so I'm going to get then minus 2L plus 2 plus a J plus 1, which gives me a minus 2L plus J plus 3 multiplied by that N. Okay, I know it looks like a really odd thing to do, but what I'm doing is I'm grouping together terms that have L plus 1s in them, and I'm grouping together terms that have N's in them, and I'm doing them in a way that you might not immediately think is the right way to do, but trust me, this is the right thing to do. And I'm going to do the same thing in the denominator. I'm going to take the L plus 1 that I'm subtracting. I'm going to group it with the L plus 1s in the first term, everything except the term that has the minus 2N. And then I'm going to group together the terms with the minus N all together. And you get in the denominator L plus 1 times 2L plus 2J plus 2 minus J minus N times 2L plus 2 plus J. Okay? Now, the numerator has a 2L plus J plus 3 common factor in both of those terms. That will cancel with a 2L plus J plus 3 in the denominator. The denominator, I can pull out a 2L plus 2 plus J term. You can see there's a common factor of 2L plus J plus 2 in both those terms in the denominator. So I can factor that term out, and I'm left with an L plus 1 minus N. And in the numerator, I'm left with an L plus 1 minus N as well. Those two terms cancel. And so in the end, when all the dust settles, I'm left with L plus J minus N plus 1 over J plus 1 times 2L plus J plus 2. But that is exactly what we said the recurrence relation was for the A 2L plus 1 J plus 1 divided by A 2L plus 1 J. That's exactly the form that it needs to be. And so we have verified this recurrence relation. All right, so now, just up to a normalization question, which you're going to answer on the homework, this establishes this recurrence relation. A2L plus 1J is minus N minus L minus J divided by J times 2L plus J plus 1, A2L plus 1J minus 1. I can then just solve this recurrence relation by looking at what happens if I replace that A2L plus J minus 1 by A2L plus 1 J minus 2 times a number, and all the way down till I get to A2L plus 1, 0. And you get a whole bunch of factorials when you do that. You get a minus 1 to the J, you get an N minus L minus 1 factorial divided by an N minus L minus J minus 1 factorial. You get a 1 over J factorial, and you get a 2L plus 1 factorial divided by a 2L plus J plus 1 factorial. Now, when you go and you look up what is a Laguerre polynomial, the Laguerre polynomial L2L plus 1 sub n minus L minus 1 of x is given by the sum j equals 0 to n minus L minus 1 of L plus n factorial over n minus L minus j minus 1 factorial times 2L plus 2j, 2L plus j plus 1 factorial times j factorial multiplied by minus x raised to the jth power. So you can see that if we pick the right value of a0 2L plus 1, we're going to get this Laguerre polynomial because we have that n minus L minus j minus 1 factorial term. We have a 2L plus j plus 1 factorial term, and we have a j factorial term. And we have a minus 1 to the j. All of the other terms don't depend on j, so they're just constants I can pull out. And then I just have to get all my constants correct in order to verify that I'm going to actually have this correct Laguerre polynomial. So what does this mean? This means that that string of B daggers can be rewritten as a Laguerre polynomial of operators that depend just on r hat. Okay? Now, we're really close to the end, but we also have to note that when we look at the coordinate space wave function, that coordinate space wave function can be written as a tensor product of a r wave function and a theta phi coordinate. So the coordinate space xyz we're going to rewrite as r theta phi. And when I take the tensor product, the theta phi goes with the LM. And recall, we did a lecture that showed that theta phi LM was just YLM of theta phi. This RNL, I just have to evaluate with a bra R on the left-hand side. But the R hat operator is an eigenfunction of that, the R bra is an eigenstate of the r hat operator. I can just replace the r hat operator by r. So there's some number that's going to come out front, but then I have this L2L plus 1 sub n minus L minus 1 of r, a function of the Laguerre polynomial, and I will have that YLM of theta phi as well. So we still need to calculate that last term. That's the wave function for the first term in the horizontal string of energy eigenstates that all have the same energy eigenvalue. And we're going to be calculating that by using the radial translation operator. Okay, that is something that's going to be done later. I believe you're going to be doing that on the homework. It turns out that that expression is e to the minus some constant times r. All right, so that's it. We are now done with the wave function for the Coulomb problem. What we found is the wave function is a normalization constant times a Laguerre polynomial times what is going to be an exponential e to the minus some constant times r times a YLM of theta phi, and that is something that you should recognize from your earlier work on the Coulomb problem. But again, you see no differential equations, and we worked it out simply by using operator relations. So in many respects, everything that we did here just came from the fact that the commutator of x with p is equal to IH bar. And again, I continue to be marveled by how remarkable this is, that you really just get everything by manipulating the operators and working with the fact that the commutator of position with momentum is IH bar. All right, that's all that we have for Lecture 10.